we're going to take a look at graphing rational functions. You might have heard the word rational in the past, talking about rational numbers, which are just numbers that can be written as a ratio of two integers. In other words, can be written in fractional form. And so we're going to see functions here that involve a fraction. And the setup for that is we'll have a function, which we could call f of x, and we can have something that has a variable in the top and something else that has that variable in the bottom. In this case, the variable is going to be x. And so we're going to have a fraction with two functions, one in the numerator, one in the denominator, and we're going to pay attention to what's in our denominator because a fraction means division, and we know we can't divide by 0. So the first thing we have to recognize is with a fraction, there's potential to divide by 0, which is not something we are able to do. And so anytime that we get a 0 in our denominator, our graphs are going to do something interesting. We're going to have breaks in their continuity, as we call it. In other words, we're used to graphs just being able to move side by side. But in these cases, if there's ever a time where we divide by 0, something's going to happen to that graph. And so let's get a brief look at what could happen. One of two things, actually. We could have what are called vertical asymptotes, which are vertical lines, right? So they're going to be vertical lines that the graph tries to get close to, but it can't actually cross it. We're going to see a couple of cases of that today. And then there's another type of asymptote, and it's a hole in the graph, and there's literally a point that just doesn't exist on the graph. And so the graph might start to go up. So we've seen graphs like this before, and all of a sudden it just can't exist here for some reason, but then it keeps going afterwards. So that would be a hole. Okay, so there's a hole in the graph. An asymptote would be a vertical line, a boundary line that the graph is going to try to get really close to, and it just can't. And same thing here. Maybe we'll see something like this. The graph, it's just right next to it, but it can't quite reach there. Okay, so what is this going to involve for us today? Well, we can type these equations into Desmos or some other graphing calculator, and we'll get a nice picture. But to get a full sense of what's going on, it is going to take a little bit of work on our part. We are going to want to factor our numerator and our denominator. So we're going to want to factor anything we can to get a full analysis here. And that's going to help us figure out when our denominator equals 0, which is an issue. We can't ever divide by 0. So after we factor, we're going to check what happens. And so that's what we're looking at here. Step 2, if a factor cancels, that is a time that we'll have a hole in the graph. Okay, so that point to where the graph just can't exist. Everything else is fine, but something about that point just doesn't work out. And so to figure out what that happens, if we see a factor cancel away, then we'll set the factor equal to 0 and we'll solve. And then we'll know there's a hole there. So we'll talk about finding the location of that hole. Once you know the x value, you can just put that right back into our simplified equation. Okay, so let's talk about what happens if a factor does not cancel. So you have something in your denominator that does not cancel away. It's not removable. Then that is a vertical asymptote. It's one of these boundary lines that the graph tries to get really close to, but it just can't go past it. And finding that location of an asymptote is the same deal as finding a hole. You set the particular factor that's in your denominator equal to 0, and now you know where that asymptote is. The only difference between these two things is a hole is a location, so we show it by an open circle, like a point almost. An asymptote, though, is a vertical line, so we write those as x equals something. So we'll put x equals a number for a vertical line, right? But for a hole, we'll show that as an ordered pair. Okay, so we'll identify the location. All right, so let's get an idea of what this looks like. So here's a general sense. If you were to type this equation in to a graphing calculator, notice we have a fraction involved where we have the polynomial x minus 4 in the numerator and a different polynomial x squared minus 16 in the denominator. So we have a variable in the numerator and denominator here. We're going to get a graph that would look like this. Now, this has a little bit of extra features that we've added in. A graphing calculator itself is not going to show this dashed line. It's not going to show this point right here. It'd be nice if it did, but it won't. Okay, so that's the work that we're going to have to do. But the rest of the graph should look that way. It should show you where the y-intercept is still, and you'll see that there's going to be these two separate curves going on. So it's a little funny looking. Let's talk about what we see. So on the graph over here, we see there's a hole, this empty circle. I'm going to change that color. So this is what we mean by a hole. It's everything, every other part of this graph is fine. It just can't exist at this point. And then that vertical dashed line is a boundary line. It's a vertical asymptote. Okay, and we're going to talk about how to find these two things. So if you recall, the steps that we said were step 1, factor your numerator and denominator. Factor everything you can. So your numerator here just says x minus 4. So we could think about that for a second, and we're going to realize there's nothing we can do about x minus 4. So we'll leave it the same. But for x squared minus 16, that does factor, right? We have that special formula. Factoring, this is a setup of a squared minus b squared. So just for a note for later, kind of remind ourselves we have factoring techniques. We'll factor as a squared minus b squared equals a plus b times a minus b, right? And so that's why the factors of this are going to be x plus 4 and x minus 4. Because a is the square root of your first term, x squared, and then b is the square root of that second value, 16, where we get the 4 and the 4. Now, what you might notice at this point is that after you've factored, we can do some comparing. The numerator and the denominator have the same factor now. And just like we do with fractions with numerical values, we can reduce polynomials as well. So if we have an x minus 4 in our numerator and an x minus 4 in the denominator, those will reduce. And we simply get 1 in our numerator now. And in the denominator, all we have is x plus 4. Okay, so let's talk about what just happened. We had two factors in our denominator. And remember, this fraction bar is a division bar. And so these are what we're dividing by. And so if there's an x value that makes either one of these be 0, we have a problem. We cannot divide by 0. So let's talk about what we've seen. We've seen one of these canceled away. We were able to reduce and cancel. That was what we said would happen if we have a hole. So if a factor cancels, you do have a hole. So let's talk about the location of the hole. The factor that canceled was x minus 4. And if we set that equal to 0, we end up getting x equals 4. Okay, so what this means is we're going to have a hole. The location of the hole is going to be at an x value of 4. If you go back to the graph over here, that's exactly what we're seeing, right? This open circle at positive 4. Okay, but a hole is an ordered pair. So 4 is the first number, but what is the second? What's the y value of that hole? Well, we want to find it, but you can't put it back in our original equation because that's going to make the denominator be 0. But now that we've canceled it, we can plug it back here, no problem. This reduced equation, 1 over x plus 4. And so we have f of x equals 1 over x plus 4. We could write that as y equals 1 over x plus 4, and replace the x value with that 4 that we just found. And what does that give us? We'll get 1 over 8. Okay, and so that's the y value of this whole, and 1/8 is a fraction, but we can tell that this dot, this open circle, is pretty low, just above the x-axis, so it's a pretty small value, and 1/8 is a smaller value as well. Okay, so that is how we find the location of a hole. Sounds easy, and really it should be. It takes a little bit of work to get that y value, and remembering that we can use this reduced equation to do that. So how do we get an asymptote? That is created by any factor that does not cancel in your denominator. So if a factor does not cancel, you have a vertical asymptote. So the factor that did not cancel is in my reduced form. It's that x plus 4. So your vertical asymptote here, which we could abbreviate perhaps as VA. Your vertical asymptote is wherever the factor that didn't cancel, your x plus 4, equals 0, gives you. So if you set x plus 4 equal to 0, subtract 4, you get x equals -4. And that should be the location of this vertical line, right? So vertical asymptote dashed line looks like it's right there at -4, which is good. That's what we found. So our vertical asymptote, x equals -4. Okay, so we've got these two different points where the graph is discontinuous. So we have a hole, and we've seen an asymptote, and that's where they come from, whether a factor cancels or cannot be canceled. And again, the reason that these things are happening are these two x values that we just talked about, -4 and +4, make our denominator equal 0, right? If I put -4 in for x down here, what's -4 squared? It's just 16, and 16 minus 16 is 0. We cannot divide by 0, so we have an issue. And the same thing happens with 4. 4 squared is 16, 16 minus 16 is 0, and we'd be dividing by 0. So another issue. Okay, and that's all there is to that. So we need to be able to identify where these asymptotes and holes are. Otherwise, everything else should be pretty familiar, right? X-intercepts are where we cross the x-axis. Now, we're not going to address it. We're not going to identify it, but you'll notice that these graphs, they start to level out to the left and to the right. There's technically something called a horizontal asymptote as well. It's this horizontal boundary that the graph is not crossing. And that boundary in this case is your x-axis. So you notice this graph is getting really close to the x-axis, but it turns out it will never cross. And this graph is also getting really close to the x-axis, but again, it will never actually cross it. So our x-intercept in this case is none. And for the same reason, that would mean our solutions here are none. So with polynomials, you recall, sometimes we have no x-intercepts and we have imaginary solutions. That is not the case here. Okay, that is something we only see with our polynomial functions in this class. Okay, y-intercept, that's where we cross the y-axis. We won't change that, and we do see that right here. So our y-intercept is in an ordered pair, 0, 0.25. So we'll put that down, and our analysis is complete. Okay, so just recap one more time. We do need to find the asymptotes and the holes on our own. That is not something a graphing calculator is going to do automatically for you. Okay, and once we have that done, we'll fill in the rest of the blanks like we have in the past. Okay, so let's talk about one more graph then. If you were to type this rational function into a graphing calculator, you're going to get something like this. Okay, And look how crazy that is. So we have two dashed lines, and let's talk about what those are. Those dashed lines, remember, those are vertical asymptotes. So here and here. So let's abbreviate that: vertical asymptote and vertical asymptote. And we could guess where they're located at the moment. It looks like this is at x equals -3. So there's my estimation. Let's see if that's true. This one looks to be at +4. So let's see if that's also true. I look around, it doesn't look like any holes are given. So let's go over here. I have this fraction of functions where we have x squared minus 3x in the top and x squared minus x minus 12 in our denominator. And we should be able to factor here. So let's talk about factoring techniques. We can factor our numerator by, so we have two terms that both have an x. So if all the terms have the same value, the same factor, then we can bring that out. And we can say factor by the greatest common factor. So if we factor this one by GCF and bring an x away from each, we'd have x times x minus 3, which multiplies back to x squared minus 3x. Okay, denominator, same thing. We need to factor it. We have three terms. And let's talk about how we have factored three terms in the past. Our strategy has been to factor by split the middle. Okay, so factor by split the middle, which you go through and find values, in this case, that multiply to -12 and add to -1. And that is going to be x minus 4 times x plus 3. All right. So those factors right there are going to cause us issues because these are what we're dividing by. And anytime these equal 0, our graph is going to have a break, either an asymptote or a hole in the graph. You might also notice that nothing cancels, right? It was close. We had an x minus 3 in the numerator, but down here we had x plus 3. So if they don't match, they do not cancel. So if we have two factors that do not cancel, we have two factors that create vertical asymptotes, just like we saw in the graph earlier, these two vertical asymptotes. So how do you find those locations? So vertical asymptote number 1. Take your first factor that did not cancel, this x minus 4, set it equal to 0, and when you solve, you get x equals 4. And that's what we said. We said it looks like we have one at x equals 4, so that was true. And for vertical asymptote number 2, we'll do the same thing with the other factor that did not cancel in the bottom. So this x plus 3, set it equal to 0. And when you subtract, you get x equals -3. And again, that is an asymptote that we had identified earlier by inspection, just by looking. So we were good guessers. We got those two asymptotes. Okay, now we also recognize that there's no factor that canceled. That should tell us that there is no hole. Okay, there are no holes here because we have no factor that cancels. We don't need to worry about that. X-intercepts, those are on the x-axis. Where do we have one? Looks like 0, 0 is one of them. And we have another at 3, 0. And there's no particular rule that I can give you right now as to how many x-intercepts you're going to have. That's a case-by-case basis. Again, it's not the same as polynomials. It's all dependent on what our numerator and denominator end up saying. And so in this case, we had part of the graph that crossed twice. Okay, and if those are our two x-intercepts, then we have two solutions, one at 0 and another at 3. And going back to what I said earlier, there actually is a way to find x-intercepts. It's when your numerator equals 0. So if you look up here, I take back what I said. We have these two x's in our numerator, these two factors in our numerator where neither one canceled. When we set these equal to 0, that's where we get our x-intercepts. So x equals 0 from this one, x minus 3 equals 0 gets you to that positive 3. So however many factors you have in the numerator will be how many x-intercepts you have. Okay, y-intercept. That's where we cross the y-axis, and sometimes we forget that 0, 0 is actually on both of those. So y-intercept at 0, 0, x-intercepts at 0, 0, and 3, 0. And that is it. This was a graph that had two vertical asymptotes. So some graphs only have asymptotes. Some graphs might only have holes. And some will have a combination of the two, as we saw in the first one. So graph these things with a calculator, but at the same time, make sure you're going through these steps of factoring so that you can get the full analysis of whether you should have asymptotes or holes in your graph.